Well, as we looked at this reaction here, hopefully this is what I ended up with. So I have some generic alcohol, and I react that with tausyl chloride. I gave you that formula last time. You don't have to memorize that as long as you remember that it's tausyl chloride. And we need the pyridine there to help pull off a proton. But all this does is substitute the hydrogen for a tosyl group, a tosylate group, and get HCl. And the only reason we're doing this whole thing is because this becomes a very good leaving group. Okay, that's just the formation of tosylate. So that's just a setup for the rest of the reactions. Once we have that formed, let's just say I have this tosylate formed. I'll just make that in black. So I can form just by reacting this again with tausyl chloride and pyridine. That replaces a hydrogen in this case with a OTS. That's a good leaving group. And now we can just use a multitude of different nucleophiles. And you've seen this before, so now we're just doing nucleophile substitution. We can substitute in this case. The nucleophile in this case that's going to substitute is what? OCH3. So I would just get substitution. I could use sodium bromide if I wanted to. If I want to replace that with a Br, that's just, in this case, the bromide is the nucleophile. So I just substitute the Br on there. I could find a very expensive way of making butane. So lithium aluminum hydride just hydrolyzes that off there. So I would form butane. Is that a very functional reaction? No, but it comes off really easy. The key is if I have a very weak nucleophile, in this case ammonia is a weak nucleophile, it allows me to substitute that onto there. So that's the key with this one. So this would be an ammonium salt plus OTS minus. So it enables us, this tosylate enables us to substitute very weak nucleophiles. We don't need a strong nucleophile in the first case, or a good nucleophile in the case of bromide. Ammonia is a very weak nucleophile, and we can actually substitute on that. Okay, so making the first step is changing the alcohol to a tosylate, and then we can do a multiple substitution reaction. We can basically substitute almost anything we want onto that place of the tosylate. Okay, so that's tosylate formation and the use of my wife tells me I stop sentences in the middle. Not. So the next thing we're going to look at is dehydration reactions. We'll actually do this in lab. Dehydration. And these are usually done with dehydrating acids. The two acids we're going to look at are dehydrating are phosphoric acid and sulfuric acid. And dehydrating means removal of water. So these remove the water. For instance, if you put sulfuric acid on your hand, it changes your hand from whatever cellular mechanism it is to charcoal. It's very, very painful. Okay? Actually, a high school teacher lost his job. He was trying to tell the students what 10,000 bee stings felt like, so he put a drop of concentrated sulfuric acid on his hand. He didn't immediately wash his hand. He had all the students do it. They did not immediately wash their hands. They have permanent scars on the back of their hand. So it's one of those things that you don't do. It sounds cool, but it's not. Another person who I think died, they were bet $500 that they couldn't down a shot of concentrated sulfuric acid. They didn't get the shot all the way down, but so they lost the bet and ended up dead. Okay, so a dehydration reaction, we react with sulfuric acid. Don't drink sulfuric acid. There's a poem that goes like that, right? An old poem. But H2O.
Larry was a chemist. The chemistry is no more. For what he calls H2O and H2SO4.
Exactly. So make sure it's a clear liquid. They're all clear liquids are not made equal, okay? So in this case, we have to add heat. This is an elimination reaction. This elimination reaction usually, for the most part, goes by E1 pathway, okay? So this is just what we had before. In this case, the leaving group is a hydroxyl group, and we also remove a beta hydrogen. So it's identical to an E1 mechanism. So in this case, I get an elimination to form that product. So it's just like before. So this is the alpha. We have a beta there, and a beta there. You only get two products in this case because there's no cis or trans in that first product. And no matter if we go through the beta on top or the beta to the right, we get the same product. There's free rotation. So we get two products in this. From what you know from beta elimination reaction, which one of these is the major product? The one on the left, using Zaitsev's rule. So these will follow Zaitsev's rule. So this is actually the major product, okay? Since it's, this is goes by an E1, for the most part, tertiary works the best. They react the easiest. That's followed by secondary. And if we really push the conditions, like really heat it up, we can actually get primaries to go by this elimination also. Though we know from chapter exam 2 that those are not allowed very well. So I could give you this reaction here, and you guys could give me all the products knowing what you know from exam 2. So again, it's beta elimination. It goes by and the other, I mean, you don't have to write this on there, but the other product is water, but I'm not worried about that. From what you know, draw all the products for that reaction. So I use sulfuric acid in the first case. I'm using phosphoric acid in the second case. Go ahead and draw the products. Tell me which one of those is the major. Sarah?
So with these, they're also elimination, but with the ones we did before, we didn't have to apply heat, did we?
What's that?
We didn't have to apply heat before.
No, we weren't applying heat before because we were using a strong nucleophile, or in this case, a strong base and nucleophile or weak base. So in this case, we're adding the acid. So what's the acid actually doing from from what we did last time? What's the acid actually doing? First, it's going to do what? If I asked you to come up with a mechanism for this, I don't have a mechanism for this. So let's go to the next page. Let's do a simple one. You actually need either sulfuric acid or phosphoric. In lab, we use phosphoric because sulfuric acid is a little more, that's one reaction that blew up on us because someone didn't do it right. So they get a little too vigorous. Phosphoric acid is a little easier to control. So product for this one. How many products did you give? 3? That's a good number. So hopefully you got that product plus that product, right? It's an E1 mechanism, so we have the opportunity for a hydride shift. So in this case, the positive charge there, initially after the loss of the leaving group, we can get a hydride shift. It can go from a secondary to a tertiary, which is that guy there, and that adds one more product besides the ones we already have, and that product looks like that. So 3 different products. The major product in this case would be just following Zaitsev's rule, would be this one. 3 substituents, 2 substituents, 2 substituents. Is that what you got? No? Okay. Tell me what's going to happen. So here's an alcohol. I'm adding a strong acid, so what's going to happen first? Hydrogen is going to pull, you got an H plus floating around out there, right? From our lone pair electrons. You guys are good at this by now, hopefully. So it's going to pull off that H plus, or attack that H plus. This is going to result in this. We know it's an E1 mechanism, so first we have to get a good leaving group. The next thing that's going to happen is Well, first off, it's an E1, so we have to get the loss of the leaving group, so our water is going to come off. I didn't draw a very good line. So loss of the water, that's going to form a carbocation intermediate. Next thing that happens in the beta elimination, E1 would be what? We have to lose also a beta hydrogen. I see lips moving. Words just not coming out. So these guys attack the beta hydrogen. These electrons go in here. And I finally form my alkene. Plus, in this case, I get my acid back again. So that would be the mechanism. Okay, a strong acid pronate. So, and before we just had a nucleophile helping to pull off the hydrogen and the leaving group left by itself. In this case, there's an addition step of adding that hydrogen to my OH.
But what is
Heat, and we just need enough energy on an energy diagram to get over that first peak, to pull off, add the hydrogen and pull off that water molecule. Vincent.
So if we did this reaction in hot water, would that dehydrate the alcohol? Because you have that small concentration of hydrogen ions?
No, you even need more than, you can't use HCl, because HCl you're going to get substitution. You need one of the dehydrating acids. These acids are good at pulling out water. In this case, they're pulling the water off the, okay? So, do another example. I don't care. How many people are already tired of organic chemistry? Only 2 more months left. Jillian, you were late on that one. You had to decide. It was going, oh.
I was keeping more.
Try another one, see if you do better on this one. This thing how smart you're getting. Let's think of college as boot camp. We push you to the limit and then over. Take the rubber band, you keep stretching it. Unfortunately, I keep going until it's straight. Such is life. Products for that one. How many products to get for that one? Dehydration reaction. We're going to lose a water molecule, an H and OH to form water. So hopefully you got that one. Hopefully you got that one. How many more are there? One more. Very good. You guys have come a long ways. You can have the cis one. Which one of those is the major product? The trans product. So the major one is this guy right here. People are scrambling writing. We already showed, did I already show this reaction? Oops. So this is the one we did the mechanism for, right? So, in sulfuric acid and heat, the product that we showed is that. But another product that can happen under those same conditions is the formation of ethers. Okay? So if we look at that last one just like we did before, again the mechanism for the first part is the same. We have an H+. Those electrons on the oxygen attack the H+. We get a good leaving group. We have a lot of this isopropanol around. So as this is leaving, another isopropanol, the electrons in the isopropanol can attack there. It can be while it's leaving or after it left. But we get something that looks like, oh, I'll flip this over. So we can get two different isopropyls, in this case reacting with one another. And the final step here is this water molecule can pull off that proton and we form our ether. Let's get our acid back again. So we can have the formation of alkenes and the formation of ether. This is one way of making ethers. Now, if I had two ethanols, I can either form the ethers to the left, two ethers and two water molecules to the left, or ethyl ether, diethyl ether, and water to the right. What's the difference between those two reactions from what we know from, this is exam 1 material? What's changing? What thermodynamic property is changing? How many molecules on the right side? 2. How many on the left side? 4. So, which one's favored under entropy? The one with 4. So this one here is a higher entropy, so it's favored on entropy. So, if you remember going way back in your memory, delta G equals delta minus delta H, is it, I forget the formula, delta TS, right? Something like that. There's a negative I'm missing. This is 2 ethenes. CH2 with H2. It is an equal sign. So as we increase the temperature, what should happen? Should I favor the formation of alkenes or the ethers? As I increase temperature, I increase the overall effect of entropy. So therefore, at higher temperature, the ethene. So we can control this at under 140 degrees Celsius. We get mostly the ether, so we favor the ether product over 180 degrees Celsius equals the alkenes. And in between there, we're going to get a mixture of products. So we can actually control this, depending if we want the ethers or the alkenes. Duncan.
Is this stuff a liquid at those temperatures?
Yeah, these are all, no. They're all gases. Ethanol will start off, so what's going to happen, you start off with ethanol, even at that, we're going to have a pressurized something or other because ethanol evaporates at 79 roughly. So this is a gas at these temperatures. So you're going to get all ether and water vapor off, but we'll do this under a pressurized system of some sort. Who's the first person that caught that? Most people go, oh, interesting. Okay, this is not the easiest way to make ethers. I already went over nomenclature of ethers, right? So, another came up with a better way. His name was Williamson, so we have the Williamson synthesis. And basically what he does is he takes and we've seen this already, this first part of the reaction, the sodium hydride. Sodium hydride removes a proton and makes the sodium alkoxide plus hydrogen gas. Now we can react our sodium alkoxide, which this is one way to make it, the sodium hydride. You can make it with sodium or potassium, but once we have this sodium alkoxide, that's not a very good plus sign. I can react that with any alkyl halide. So X is any halide, iodine, bromide, chloride. These react to form an ether plus sodium, whatever halide we have. So this is a lot more economical or higher efficiency reaction. The key to this is the alkyl group attached to the halide cannot be sterically bulky. So again, you can write this as double arrows, or I can do number systems. So sodium hydride reacts first. The next thing we're going to do is react that with an alkyl halide, ethyl chloride. Draw the product for that reaction. So as soon as you see sodium hydride followed by an alkyl halide, you know this is a Williams synthesis. So you're just connecting the two alkyl groups with a oxygen. So on one side, there's 3, and on the other side, there's 2. Again, with a lot of these times when you're connecting molecules, make sure you count your number of carbons that you started with should equal the number of carbons you ended with. This can be written different ways, so I'm going to write the other way this time. So instead of numbering system, I can go arrow, arrow. Duncan.
How bulky is too bulky for the reaction to go?
Yes. If I'm going to give this to you, I'll make sure they're not. I mean, that's beyond the scope of this class. That's just if you're doing the chemistry, you just can't have them. Like tert butyls will be too bulky. Now, if there's something, if it's like a. Now the key is if you want to connect the bulky thing, you put the bulky thing on this part of the molecule and not on the alkyl halide, and you can get it. But there is a limit. The reactivity goes down as that bulkiness of the group gets bigger. So a lot of times we just add like ethyl or methyl groups to it. So in this case, hopefully you got something that looked like this. Is that what you got? We're doing good today. Williams synthesis. So it's an easy way of making ethers. Once we have an ether, we can do an acid cleavage. So an acid cleavage, there's multiple hydrohalic acids we can use. I'm only going to focus on one of them, and that one is going to be which one do I use? HI. So you need excess HI. This works with HBr, not as well as with HCl. And again, we have to heat this up. It cleaves the ether bond, and I form in this case RX or RI. So two different RIs. One's an R primes and plus H2O. So the key here Again, people can, you see an ether reacting, and I'll be sure to put excess HI on there, so you know it's not a substitution reaction, or looking at some kind of other reaction in this case. So in this game, we can just take the ones we had before, react these with excess HI and heat. You're going to cleave the ether carbon oxygen bond on either side. Replace those bonds with CI bonds. So in this case, you get two products, one propyl iodide plus ethyl iodide. Again, I'm not interested in a water molecule. I'm only interested in the organic products. Questions? Oops, excess heat. Go ahead and do that one. Correct name for that one is? This one's easy. 5 carbons with an iodine in the 1,5 position, so 1,5-diiodo pentane, right? So all we are is breaking these bonds here and putting I's on where that oxygen was, and the water comes off. So. Okay, and I'm just making up problem because you guys are struggling a little bit. Find 2 different ways of making this guy. Oh, no, let me just do this one. I want the starting material upon acid cleavage, you form 2 of those groups. 1 molecule. Give you a hint, it's a 6-membered ring. See a lot of scrunched up faces. Is that what you got?
Yeah.
Good job. What, that was the right answer. You got let's make something a little more complicated. Let's see how complicated I can get this. There you go. Draw all the products of that one. It's not that hard of a problem. Just cross off all the carbon-oxygen bonds, and those become carbon-hydrogen bonds. So every oxygen becomes 2 iodines, and they're not connected in the middle. So it looks complicated, but it's not really that complicated of a problem. Just look at the little spots on it. So let's do the cleavage. You're going to go there, an I there, connected an I there, I there, I there, I there, I there. A lot of I's. And then start writing those pieces together. I mean, it looks like complicated, but it's not that complicated. One of the products is methyl iodide. So this is, our products is this portion here. It contains 2 carbons. On one of those carbons is 2 iodides. And on another carbon is 1 iodide. Next portion is this guy here. That's 3 carbons. 2, 3, with an iodide on each one of the carbons. Then finally, the last product is a cyclopentyl ring with an iodine. So it looks pretty complicated. As long as you keep track of how many carbons are in each place and what's connected to them, it's not really that hard of a problem. Did I do it right? Always do your math. I have 1, 2, 3, 4, 5, 6, 11 carbons. 1, 2, 3, 4, 5, 6, 11 carbons. Is that what you guys got? If Katie got it, then it must be right. Some people are still struggling with that one. Maybe that's a good test question. Review question. We've seen these already. Followed by an acid workup. This is a what sort of reaction? Grignard reaction. So the Grignard reaction, we form carbon-carbon bonds. We always form carbon-carbon bonds, single bonds, and we're always going to have the formation of a hydroxyl group. So this should be review. We did this a while back. You should get the correct name for the product. In this case is 1. That's a 1. Oh my goodness. 1-butanol. Okay, are we really this lost, or are we this quiet today? Bad weekend? Bad weekend, okay. You're lost, okay, you're honest anyway. Crystal.
I have a question with the top one, the 2 products with like, the 2 products that are like the one with the 3 eyes.
Both of them with the 3 eyes?
Yeah, like, I thought, were they the same? Like, why
No,
is one?
so the first one here, it says 2 carbons on the left-hand side of the ring system. There's only 2 carbons in that section connected to 3 oxygens, right? So originally there's 2 carbons, those 2 inside the ring circle are connected to 3 oxygens.
So that one's the one on the top.
That's the one on the top right. And then the other one is a 3 carbon chain, and it's actually connected to 1 oxygen on each of the 3 carbons. So we replace those oxygen in that case with 3 iodides. Okay?
And that one's the other.
And that's the other one. So this one, the second member of the Taylor reaction, this is a Grignard. What is this called right here? That's an epoxide group, right? So at this point in time, I've been very nice to you because I just gave an epoxide that was 2 carbons and an oxygen. So we can have nucleophilic attack, which this is actually a nucleophilic attack I just showed you. But what happens if I gave you something like this? And I had some nucleophile, strong nucleophile, and we follow this by, in this case, I just need water, but a protein instead. I can get one of 2 products. I could get this product, or that product. And this is going to depend on what? Strong the nucleophile is. So is it going by an SN1 pathway or an SN2 pathway? So we're going to say this is a strong, so this is going to go by an SN2 pathway. So if this is an SN2 pathway, is the nucleophile going to attack here or here first? Or where's it going to attack? What's the nucleophile? The nucleophile is going to come, it has some size. Is it easier for it to attack at a crowded area or a more exposed area? More exposed area. So in this case, this undergoes an SN2 pathway, so we do not see any of that one. We only see the nucleophile attacking at the least hindered or the more accessible carbon. Okay? Okay, it's going to attack from the least sterically hindered side. How about if I put this in a ring system and asked you to some strong nucleophile followed by water to protonate the oxygen? Draw what you would think would be the correct one. Knowing this is going by an S and 2 pathway, draw what you would think the product would be. So in one of those carbons, in this case, they're both the same. That's supposed to be a wedge up to tell you that the epoxide is coming on from the top side. Okay, so in this case, I put the hydroxyl side coming up. The nucleophile is going to be on the other carbon. Is the nucleophile going to be coming from the top side, or is it going to be coming from the bottom side, or we don't know? It's going to be from the bottom side because from an SN2 pathway, we always know we have backside attack. It'd always be backside attack. So in this case, the nucleophile, we only get one product. And again, I'm not worried about this. You're going to get the enantiomer also. I mean, it could be the other direction. It goes off the other side where the hydroxyl group's wedged down on the bottom, wedged up on the top, and the nucleophile is wedged down on top. So you're going to get both of those, but we're always going to get backside attack with a strong nucleophile. So now let's put both of those together with the plus. So there's my nucleophile. In that case, my nucleophile is methoxide. That's going to be followed by a workup in water. Draw the correct product of that reaction. We've got two things going on here. We know it's going to attack from the nucleophile is going to attack the least substituted carbon. And it's going to end up on the, what side of the hydroxyl group? Opposite side of the hydroxyl group. So the hydroxyl group going to end up at the green carbon or the yellow carbon? The green carbon. And since I left the methyl group coming out, the hydroxyl group has to go back. That tells us the nucleophile, in this case OCH3, has to be coming out. So that would be the correct product. Questions? So one more example. That's a bad. Again, nucleophilic attack. In this case, my nucleophile is going to be what? What group? An SH. So my nucleophile is the SH group. It's going to attack from the sterically unhindered side, so it's going to attack from the one end. So in this case, again, I have 4 carbons. It's going to be H on that side, and on this side is going to be a SH. Oh, not a SH. Again, in this case, I'm not really worried about this, but I'm just trying to, this is actually a asymmetric carbon, so we have the chance of getting R's and S's, but I'm more interested at this point in time that you know that the thiol group attacks from the least sterically hindered, forming a hydroxyl thiol group. Okay, that's what I'm looking at here. Questions? Next problem. Whoops. So here's an acid, strong acid. Mechanistically, show me how to get from those reactants to that product. So now in this case, we're not forming we don't have a strong nucleophile. It's not a nucleophilic substitution SN2 method. Okay? First thing that has to happen on this is what? What's that? We have to get a better leaving group. So how have we been getting a better leaving group on oxygen at this point in time? Addition of the hydrogen. So what we see here is these electrons grab that hydrogen. Those electrons go on completely onto the bromide. When that happens, I form, whoops. So now I need to break a carbon-oxygen bond. I have 2 pathways to do this. I can either break, these electrons go up here, or these electrons go up there. So on the green side, I just draw it in green, it would look something like this. And on the blue side, the opening will look something like this. And from what you know of organic chemistry up to this point, which one of those would be the favored one? The green one. Why? Secondary carbocation versus a primary carbocation. So in this case, what kind of mechanism pathway we're following in this case? It's going to be a SN1. Okay, so the formation of carbocation, we're going to have that. Now, with our bromide, knowing that we're only going to form the secondary one, in this case, these electrons here will attack my secondary, and I'm going to end up on my product there. Okay, so we get a different attack depending on if we're using a strong nucleophile that goes by an SN2 pathway, or a strong acid which goes by an SN1 pathway. Okay, so this is why we teach you SN1, SN2, so you can kind of discern these 2 different pathways. So draw me the product of this reaction here. Remember, carbon stays the same. The OH group's gonna end up on the, what classification of carbon, tertiary or primary? Leaving the bromide on that one. One more example. We'll be done for the day. Yes, Sarah.
How do you determine where the OH group
The OH group
goes?
has to go on either one. So on this, in case on this one, it can either go there or there, right? Because the oxygen's connected to either one of those.
Does it have preference over?
It has preference because we form a carbocation intermediate, so the carbocation will always go on the more substituted, meaning the OH will always go on the least substituted in this case. So in this case, the OH is going to end up on the bottom one, the yellow one. That leaves on the top one's going to be the Br. Now this goes to a carbocation intermediate, so we're going to get a mixture of products in this case, right? It could be just the opposite, right? So we can get this and it's in the enantiomer. So we're not going to worry about that at this point in time. Okay? I haven't finished chapter 9 yet. I got thiols to talk about. We'll talk about those on Wednesday and we'll go right into the NMR.